In pursuit of sharing technical knowledge and to support new engineering entrants, I, Pranav, will be presenting today's presentation on Power Transformer Part 82. As the topic is of the continuation, so for your convenience, the link of the previous session is given under the description box. Let's start with effect of high molecular weight acids on transformer insulation. High molecular weight organic acids produced by the oxidation of mineral transformer oil during service life are primarily composed of naphthenic acids and higher carboxylic acids like stearic acid. From the analytical point of view, naphthenic acids are generally considered more injurious to transformer oil than higher carboxylic acids like stearic acid. Naphthenic acids and stearic acids are both organic carboxylic acids formed during the aging of transformer oil, but they differ significantly in their origin, chemical structure, and impact on oil service life. While both are acidic byproducts of oil aging processes, naphthenic acids are specially identified as highly corrosive to the transformer's internal metal components, that is copper and iron. Key structural features of naphthenic acids. Naphthenic acids are naturally occurring constituents of crude petroleum formed over geological time. During refining processes, most of the acidic and polar impurities are being removed to improve oxidation stability, although trace amounts may remain. Mineral transformer oils, despite undergoing high level refining, experience significant chemical aging during prolonged service period. The aging occurs due to continuous exposure to oxygen, heat, and contaminants. The process is primarily driven by oxidation, which initiates and accelerates the degradation of hydrocarbon structures. As a result, various oxygenated byproducts are formed, including carboxylic acids. The presence of moisture and metal particles, particularly copper and iron, acts as a catalyst in the oil oxidation process, which is thereby significantly accelerating the rate of acid formation. In particular, copper is especially problematic as it reacts with acids to form soluble copper soaps, which further enhance catalytic activity. The phenomenon leads to a self perpetuating or autocatalytic cycle in which the degradation products themselves accelerate the continued breakdown of the oil. The resulting acidic species constitute a complex mixture of organic acids, including one, low molecular weight acids like formic, acetic, and levulinic acids. Number two, modified or oxidized naphthenic type acids. Number three, higher molecular weight acidic compounds like stearic acid. Naphthenic type acids are predominantly structured by one or more saturated cycloaliphatic rings, that is 5 or 6 membered, attached to a side chain containing a carboxylic acid group, that is COOH. The naphthenic acids are represented by the formula CnH2n plus Z O2, where N indicates the number of carbon atoms, which is nearly 8 to 30, and Z is 0 or a negative even integer, that is 0, -2, -4, -6, up to -12. That specifies the hydrogen deficiency resulting from ring formation, that is number of rings. Naphthenic acids are often characterized by their structural ring count, that is Z number, rather than a single specific molecular structure, which is as follows: Z equals to 0, that is saturated acyclic acids, fatty acids. Number 2, Z equals to -2, that is monocyclic naphthenic acids, that is one ring. Z equals to -4, that is bicyclic naphthenic acids, that is consists of two rings. And Z equals to -6, that is tricyclic naphthenic acids, that is of three rings, and so on. Therefore, Z is the index of hydrogen deficiency. Naphthenic acids is formed due to the degradation of mineral transformer oil or a complex mixture of carboxylic acids. Depending on the structure and degree of oxidation, their molar masses, that is molecular weights, are typically ranging from 120 to over 700 grams per mole. However, naphthenic acids within the 180 to 350 gram per mole range are particularly significant as they contribute substantially to oil acidity, thereby increasing the total acid number, that is TAN value, and potentially leading to sludge formation and corrosion of transformer internal components. Leading to sludge formation and corrosion of transformer internal components. These fractions are particularly impactful because the acid molecules exhibit sufficient solubility and mobility in oil to chemically interact with metal surfaces, that is copper and iron, thereby promoting corrosion, including in some cases the formation of copper sulfide. Naphthenic acids with a molar mass range from 180 to 350 gram per mole are typically composed of 9 to 20 carbon atoms, that is within the C9 to C20 range. Naphthenic acids with molecular weight below 180 gram per mole are generally more volatile and be less persistent in the oil phase. Conversely, those above 350 gram per mole exhibit lower solubility and a greater tendency to form sludge or precipitates rather than actively participating in reactions that lead to corrosion of internal metal components. Key structural features of stearic acid. Chemical formula of stearic acid is C18H36O2 or CH3, CH216, COOH, and its molecular weight is 284.484 gram per mole. It is a high molecular weight, long chain saturated fatty acid that forms in transformer oil primarily due to the oxidation of hydrocarbon molecules under thermal and electrical stress. From the molecular structure, it is to exhibit following features. See the structure of stearic acid, C18H36O2. A. Configured with a linear, unbranched, saturated hydrocarbon chain consisting of 17 carbon atoms in the chain plus one terminal carbonyl carbon, totaling 18 carbons. B. At the chain contains only single covalent bonds and no double bonds between carbon atoms, which makes the acid molecule stable, straight, and allows it to pack closely. Number C, a polar carboxylic acid group, that is COOH, is located at one end of the chain, rendering it acidic. Stearic acid is amphiphilic in nature because it consists of a long hydrophobic hydrocarbon tail and a hydrophilic polar carboxyl head, which allows it to adhere effectively to metal surfaces. Naphthenic acids and stearic acid formation in transformer oil, which one is more injurious in transformer insulation system? One, naphthenic acid and stearic acid as high molecular weight organic acids formed during the aging of transformer oil possess distinct detrimental effects on the overall insulation system. Number two, naphthenic acids as a mixture of cycloaliphatic carboxylic acids naturally present in crude oil characterized by their ring structure. Naphthenic acids act primarily as highly corrosive agents towards metal components, copper and iron, while stearic acid acts at 18 carbon long chain saturated fatty acid that contributes significantly to oil oxidation and sludge formation. Corrosion process of naphthenic acids metallic components. In oil immersed transformers, as naphthenic acids accumulate and react with metal ions, specifically iron from the tank or core or oxygen, they form iron naphthenates, which are oil-soluble corrosion products, while copper naphthenates are typically formed by the reaction of naphthenic acids with copper compounds, that is winding materials, The formation of iron naphthenates leads to several detrimental effects on the transformer performance and lifespan. These include one, catalytic oxidation of oil. Iron naphthenates act as powerful catalysts that accelerate the further oxidation of the transformer oil, leading to create a vicious cycle of increased acidity, sludge formation, and degradation. Number two, sludge deposition. Iron naphthenate is a complex mixture of ferric, that is Fe3, and ferrous Fe2 salts derived from of mixed carboxylic acids. These salts are generally oil soluble, but under high temperature conditions, that is above 180 to 200 degrees centigrade, or in high electric field zones, they may decompose or precipitate as solid deposits, resulting in the formation of highly viscous and sticky sludge from naphthenate soaps. That is iron naphthenate soaps, sticky sludge, iron naphthenate soaps. Thermal decomposition is often considered part of the naphthenic acid attack on steel, leading to the formation of iron oxide or magnetite scale, along with sticky sludge composed of iron naphthenate soaps. Number D, while under electric field conditions, while under high electric field conditions, iron naphthenates can be driven out of the oil phase, which promotes the formation and deposition of these sticky metallic soaps. Heat transfer efficiency. The deposition of sticky sludge can adhere to core, winding, and metal surfaces, increasing a risk of partial or complete blockage of oil ducts within the core and windings. This restriction in oil flow rate significantly disrupts the natural convection cooling system of the transformer, leading to localized overheating and an overall reduction in cooling efficiency. Number C, increased temperatures caused by inefficient cooling accelerate the thermal degradation of the paper insulation on the windings, thereby reducing the overall service life of the transformer. Number 4, oil quality degradation. Under high electric field conditions in transformer system, iron naphthenates may precipitate out of the oil phase, leading to changes in the physiochemical properties and overall performance of the insulating oil. Number 5, formation of conductive paths. Iron naphthenate is a metal organic salt composed of a central metal ion, that is ferric or ferrous, bonded to the carboxylate group of naphthenic acids, COO. Because of the carboxylate group, iron naphthenates are indeed partially polar and of limited solubility in non-polar transformer oil. Precipitated iron naphthenates can form an acidic sludge containing polar molecules and ions within transformer insulation systems. Under high electric field stress, these polar spaces undergo dielectric polarization, aligning their molecule dipoles. This leads to localized charge accumulation and promotes the formation of semiconductive paths. As this acidic sludge accumulates, often in combination with moisture, it can facilitate the development of conductive bridges between energized windings. The significantly aggravates the situation by enabling a progressive increase in leakage current between conductive parts. This significantly aggravates the situation by enabling a progressive increase in leakage current between conductive parts. The resulting leakage currents cause localized heating, which can initiate partial discharge. Over time, this process accelerates the degradation of both paper and oil insulation, ultimately contributing to progressive insulation failure. Points to be noted. Strong electromagnetic field, especially in case of high voltage transformers, accelerates the migration of oil-soluble charged metal acid contaminants toward high field regions where they concentrate and precipitate. Therefore, these contaminants may have to accumulate between coil segments on high voltage windings. In the context of general transformer oil acidity, it is important to note that the stearic acid C18H36O2 is typically a long chain fatty acid and is not normally present in oxidized petroleum derived mineral oil. It is actually exhibited in the vegetable oil. Mineral based transformer oils consist mainly of paraffinic and naphthenic hydrocarbons. When mineral based transformer oil oxidizes due to heat, oxygen, and catalytic metals, it primarily produces naphthenic acids and low molecular weight carboxylic acids such as formic, acetic, and levulinic acids rather than stearic acids. Naphthenic acids and low molecular weight carboxylic acids such as formic acid and acetic acid are key contributors to corrosion and accelerated aging of cellulose insulation. They also indirectly promote sludge formation by accelerating oxidation and polymerization processes. Naphthenic acids are major contributors to total acid number, that is stand value, in aged mineral oil based transformer oil. Organic acids, including naphthenic acids, can also facilitate polymerization reactions, especially in the presence of moisture and catalytic metals, thereby contributing to sludge formation. Oxidation byproducts like naphthenic acids contain a carboxylic functional group, which makes them polar and capable of interacting with water and metal surfaces. Iron naphthenate is a metal soap formed from naphthenic acids and iron. It is also Amphiphilic, also amphiphilic as because its hydrocarbon tail is nonpolar while its metal carboxylate head is polar. Now, the interfacial tension measures the oil's ability to separate from water. The presence of polar compounds such as naphthenic acids and iron naphthenate would thus to reduce the interfacial tension in transformer oil by accumulating in the oil-water interface and weakening cohesive forces within the oil molecules. Naphthenic acids are widely considered more injurious in transformer insulation systems than stearic acid because they are recognized as more chemically aggressive, possesses higher oil solubility, and number 3, combined effect of high chemical reactivity and solubility. The more chemically aggressive the situation that prevails, high reactivity with metals, as for example, copper and iron, actively contribute to the formation of conductive sludge and corrosive metal naphthenates, act as pro-oxidants which facilitate the oxidation of hydrocarbons, reducing the oil's oxidative stability, possess higher oil solubility that facilitates their persistence in the oil phase, promoting sustained interaction with metallic surfaces and leading to the formation of metal naphthenates that contribute to corrosion and insulation degradation. Combined effect of high chemical reactivity and solubility would cause readily react with metallic components to form metal naphthenates which promote corrosion, catalyze oxidation reactions, and accelerate the overall degradation of the insulating oil. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also, share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you for patient hearing.